it was what is there as the length contract and the time interval delayed going from one frame to the other, one could ask, is there a quantity that is invariant? Yes, the quantity is invariant is the following. It means if you change this quantity in any frame, it will remain the same. When I put a prime, I mean I am in a moving frame. And so now if you change frame again, it's not derivative. This it means I'm going from one frame to another frame that I label prime, to another frame that I label double prime, and so on. So this is an invariant. And yesterday we proved that is invariant. And you know, you can write these, well, also if instead of taking the point, you take the space interval and the time interval between two events. Also, this is invariant. That means delta x prime square minus c square delta t prime square is invariant. And you know, as you have seen, the Lorentz transformation mix space and time. So this is a sort of a space-time invariant, but it's very important that there are some absolute quantity, like in Galilean relativity and Newtonian mechanics, time was the absolute quantity that did not change in going from one frame to the other. In special relativity, we have seen that because of that postulate that says the velocity of light is the same in any frame, you know, the velocity is a relation between x and t. And then if it is the same in any frame, it relates x and t in any frame. So automatically in special relativity, you have a relation between x and t, and is embodied by this relation, saying this quantity or this quantity don't change under transforming from one frame to the other. Now, which is the meaning of this? You know, many people, if you write in this manner, they call it proper distance. Other people write this quantity in this manner, delta t square minus delta x over c square is the same with a different sign, and then the dimension is time, so this is proper time. Now, what is the physical meaning of this proper time? You see from here, and we will see in the next lecture, you know, if you are, imagine you have a particle moving with velocity v, and if you stay across that particle and yourself move with velocity v, then delta x is 0, okay, and then the proper time is this delta t, okay? So that means if we go to a frame, let's call a frame in which delta x is 0, because we are sitting together with the particle, so there is no displacement. The particle does not, it is as if it were moving. Then, so the proper time is the time that you measure when you move at the same speed as the particle you are following. These are displacement of particle, okay? So it has a meaning of proper time not only because it has the dimension of time, this expression, but also because it is, so proper time is the time you measure once you move with the particle whose motion you are describing. Okay, this is the physical meaning. Now let's see if, what else can we say? Yes, yesterday we said that this distance can be of many type. It can be space-like distance, this interval, this invariant quantity can be, okay, if we x and t, then let's draw this line. This is x equals ct. Okay, this is the origin. Let's take three different points, B, C, and A. Okay, then if we measure the distance OB, this distance OB, delta x square minus c square delta t square, you see that this is this quantity is positive because delta x is bigger than c delta t. So this is a space-like distance or interval. And you see these two, they say they are causally disconnected. O and B are causally disconnected. It means there is no signal traveling at a speed, at most the speed of light, that can reach B starting from O in an interval of time delta t. You see the distance is much longer than the one that would be covered in an interval delta t by the speed of light. So these are causally disconnected. Now let's say take O and C. This point lies on this equation. So this is 0, and this OC is a light-like distance. And of course, C can be reached by O when we move at the speed of light. Third case, so the third case is OA, delta x square minus c delta t square is less than 0. You see the time part is bigger than the space part. This is called time-like distance. And this can be, point A can be reached from a signal leaving O at a speed that is less than c. Okay, so this is where most of the events take place. Means two events that are related one to another take place in this area, and this is called light cone area. If you are outside the light cone in this area, you cannot connect causally two events. This is very important things. Now, one more thing I wanted to tell you is the following. You see, if we say that under a Lorentz transformation, that means sometimes what I call Lorentz transformation are actually boost. That means change of velocity from one frame at rest to another that moves with v. We have that this quantity is invariant. Okay, but if you look, this quantity, let's suppose we are not just in x but in 3 dimensions, then this quantity would be delta x square plus delta y square plus delta z square, and this would be the square of a distance, and this invariant under rotation. Okay, so you see these objects look also like a sort of distance, but it has this strange minus sign here. So a manner to write, for example, this, so this invariant under rotation, this is invariant under, instead of saying Lorentz transformation, let's say Lorentz boost. Lorentz boost, it means a change of velocity, the one that we analyzed yesterday. Now there is a common manner, also this is a distance, a pseudo distance in space-time. So this is the square of a pseudo distance in space-time. In fact, distances in general are in a space of n dimension, how you introduce distance. Distance is what is called a metric concept. So basically, if you have some distance delta L, usually it is Gij delta xi delta xj, where this is a sort of matrix, and you know, to reproduce, for example, this. So in general, you indicate in this manner. So I goes from 1 to n, so you are in an n-dimensional space. And then a distance is an object like this, where this Gij is a symmetric m by m matrix. And is called metric. So the metric is the crucial ingredient that we need to get a distance. Now let's look at the rotation. Let's suppose we are n equal 3, and let's take the usual distance. Sorry. The usual distance, this one is delta x square plus delta y square plus delta z square. So we could write it as a Gij delta xi delta xj, okay, where the index I stays for x, y, and z. Let's call it, instead of calling x, let's call it L. Okay, and then the metric is a 3 by 3 matrix, 1, 1, 1. So it's a diagonal. It's a diagonal metric with all indices 1. Let's now take this, so this is in the case of rotation. Let's take these strange things that are invariant under relativity. Can it be put into this same form? Yes. So if we call this object, I don't know, let's call this object, we call proper time before because it was the other way around, but it doesn't matter. You will see many forms of this metric. So let's call this delta S square. Actually, here is delta L square. And then can it be written as G mu nu delta L mu delta L nu? Yes. You take a 4 by 4 matrix made in this manner, 1, 1, 1, minus 1, all the rest 0. Okay, it's a 4 by 4 matrix of this form. And delta L1 is delta X, delta L2 is delta Y, delta L3 is delta Z, and delta L4 is C delta T. You see that then it has this form, again a metric and an interval of time. If we want to take this away, just put the square. So it has a common structure. So this is what they call a 4 distance in space-time. And it is invariant only if here there is a -1, that means here is a -1. Sometimes they do the proper time, so they take the opposite of this, and then what you get is a different metric, where you have 1, -1, -1, -1 is a question of convention. I will go from one convention to the other. So you see, if you write C, let's put in this manner, delta T square minus delta X square, then this is the interval of proper time. And then this one you can write as a G tilde mu nu delta L mu delta L nu. But now the G tilde mu nu is a metric that in this case is 1 minus 1 minus 1 minus 1. Okay, so there are different metric producing either these or so. It depends if you look at these things as an invariant interval of x or an invariant interval of time, if the dimension that you wanted. Sometimes the fourth component, that is time, instead of being the third component, is the first one. And then what they do, you see here, the time is the first component. And then they call the first component 0, 1, 2, and 3. So that means if you find G00, 0, it is this, okay, is the first. So the 0 is the 0 or the fourth, according to which convention you use, is associated with time. But we will go many times through this, so don't worry about this. Now, the next chapter we will do is about dynamics, and I will send afterwards to your colleague the notes. We will do 2 chapters on dynamics. That means today and next week we will talk about dynamics, because as in classical mechanics, also in relativistic mechanics, we will have to define the concept of momentum, conservation of momentum, conservation of energy, and so on. I want you to remember one thing. The proper time, that is the time we measure once we move with the particle whose motion we are describing, is a relativistic invariant. That means this object does not change. This is very important. Now let's, the next concept that we will define is the one of momentum. And this is a concept that has created some trouble. Okay, so we will describe momentum. And what do we want of momentum? Well, some relativistic momentum. We want that when V is much less than C, goes in the usual non-relativistic or Galilean momentum. And second, we want that P is conserved. And you can say, why you want that P is conserved? Well, you know, conservation law, most probably you have done in classical or quantum mechanics. Conservation law are related to symmetry principle. So the symmetry, thanks to the theorem due to Ennio Noether, and then behind the conservation of momentum, there is the invariance under translation. Okay. So how many are you altogether? 6, 4, 10, 15? Okay. So these are the two things that we want, that is conserved and that in the non-relativistic case goes into. Let's take the most naive one and we will go into some trouble. Let's study the following scattering event. Let's take X and Y. Let's take two equal mass M moving this way, another symmetric particle here with mass M moving to the same direction, then they will scatter. They will scatter and move away. Like that. Okay, so we have these two particles, these two spherical balls that they hit each other. They are moving with the same velocity, v, that has a component vy and a component vx. So a very simple example, the same v. This is minus Vy, this is minus Vx. Let's call this particle 1 and this particle 2. And we know that what happens is there is a scattering in this direction. And because of, let's suppose non-relativistic things, if you do, you get just the angle change, but the velocity, because of conservation of energy, is remain the same. Now let's analyze this. Now, so I will not analyze it at the non-relativistic level because it is a simple example that for sure you have worked out by yourself. So two particles are coming, they hit each other, and they move away with the velocities the same magnitude, okay, but different angles. And now, the total relativistic momentum is conserved. That means if we take the p at time equals 0, the total p at time equals 0, you know, the total p at time equals 0 is 0 because one momentum is opposite to the other. And if we take the total t after they have scattered, so at t equal, let's suppose, an interval time. So this is time equals 0 when they start, and when they go away is time equal time. The total is again 0. Okay. Now let's look at the change, for example, for particle 1. Particle 1 is this, that does these things, and particle 2 is this, that does these things. Let's go and look at the change in the y component of particle 1 of the momentum. You see, first it had minus v and then it goes plus v. So altogether we have to take this one minus this one and you get 2m v1y. This is the total change in momentum between instant time 0 and instant time equal t. Now, if we take delta p2 y, so this does this way, but this way you see that vy is negative. So this one is minus 2m v2y. But v1 and v2 are the same. So if you sum the two, you see the sum of these, sum delta py plus delta py2, the sum is 0. Okay, and this we are in the rest frame in which we look at the particle moving. Now we should have the same thing, conservation of momentum and so on, also if we change a frame. So let's change frame and let's put ourselves in a frame in which we move with this particle too. Okay? So here momentum is conserved, at the initial is 0, at the final is 0. We look at the y component and we got also 0 because this is a conserved quantity, but a vector-like quantity, so it's conserved. And this we are in the rest frame. Now let's go to a new frame, to a different frame. Let me, okay, I have to cancel. So now we go to a new frame, S prime, in which we move with this particle at speed. So this, the velocity of this is equal to the Vx of 1, of particle 1. If you remember yesterday, we worked out in a new frame moving all the velocity along y change. Yesterday we built a formula that was omega prime equal 1 omega y 1 minus omega x v c square 1 minus v square c square. Yesterday we said all the vertical velocity of a particle change if we go from a frame. So W is the velocity of the particle, V is the velocity of the frame, and we work out this formula, okay, yesterday. That means different than in the non-relativistic case. In the relativistic case, even if you move along x, there is a change in the velocity along y, and this was the formula. Now we will have, let's look, in our case, this is the velocity of the particle, but we call it Vy. So V prime y is equal to Vy 1 minus, and okay, this Vx is Vx, and this V is the V of the relative velocity between the two frames. Okay, so this is the formula we have adapted to our case, but to now, we have chosen, so this is the velocity of the particle, and in particular of particle 1. We have chosen now to move the velocity between the two frames is the same as the one of particle 1. That means what we have now, we don't have that picture anymore, but we have this picture. We have particle 2 moving with m, v prime 2, and we have particle 1 moving with vy prime 1. So we are in a frame that moves with the second particle. So basically the velocity along x of particle 2 is 0, so it has only velocity along y, and it sees the other particle coming. So this is at time t equals 0. Then there is a scattering, and at time equal t, what we will have is we will have the particle moving in the opposite direction. So this is particle 1, and this is y component. Now let's do the calculation. You see that I have indicated different arrow with different length. Let's do the calculation and see what happened. So we are in a frame that moves with the second particle. Okay, so let's use this formula. Okay, let's remember that we have chosen the relative velocity to be the one of the particle 1, so Vx of the particle 2. So let's now insert this formula for particle 1 and particle 2. Okay, so we have that V1 of x is minus Vx, okay? Because we are, remember the picture that I had before, the particle 1 has a Vx that is opposite of the normal Vx, and V1y is minus Vy. Particle 1 is the one. Don't look at this picture that is in the new frame. Let's look in the old picture. Then let's use this notation into this formula, and we will have that V prime of y of particle 1 is equal, I insert there, Vx is Vy is minus y. Then I have this one, Vx is minus Vx, and V is Vx. So basically I have plus Vx squared over 2, 1 minus Vx squared over c squared. So this expression becomes minus Vy 1 plus Vx squared over c squared, 1 minus Vx squared c squared. And there is 1/2, let me... No, there is no 1/2. So on page 3 there is a mistake. Yes, let me double check. No, there is a 1/2. So yeah, there is a 1/2. There is a 1/2. So this is the velocity of particle 1 along y in the new frame, that is the frame that moves with velocity Vx, the same velocity as the first particle. Let's go and see now V2, y, the y prime of particle 2. Okay, now let's take that formula. Vy is Vy. Okay, and then we have 1 minus Vx squared over c squared, because the particle 2, okay, we have to put on the left-hand side, on the right-hand side the same. So particle 2 was moving in the former frame with Vx, and this is Vx, so you get a minus. Here instead you get a plus, okay, using that formula. And then you have 1 minus Vx squared c squared 1/2. Okay. Okay, so on page 3 of the note that I have already prepared to send, there is a 1/2 missing in that things. Now you see why I draw the two vectors different. The two new velocity of particle 1 and particle 2 are different. This one has a plus, this one has a minus. And the reason is that I had to, for particle 1, I had to put here particle 1 is Vx, okay, and the same for particle 2, and of course they are different. Now, so this is very important, this difference in sign. Now, because let's look what happens is this kind of scattering, and they go back. So let's see the total change in momentum for the particle 2. If we look at the total change in momentum of the particle 2 is 2 times this. This is the total change in momentum of particle 2 along y. And this, and then it's 2Vy, 1 minus Vx squared, c squared, 1 minus Vx squared, c squared, 1/2. But let's look now at the, where do I write? No, let's write here. Let's look at the total change in momentum of particle 1 is here. And I will have before and after, I have the same, but 2vy 1 plus vx square c square 1 minus vx square c square 1/2. So you see, these two changes are not equal. That means there is no conservation of momentum. Okay, yes, please.
The change in momentum from particle 2 along y is minus 2m dy.
This one is 2 times this.
With a minus sign y?
Let me see. Plus, minus, you are right. After and what? Okay. But beside this sign is these different things that makes them different. So basically, the variation is not the same. So this is the total variation in particle 1. This is the total variation in particle 2. The sum of the two should be 0, but it's not. So it means that with the definition of momentum, the naive definition of momentum we have used, momentum is not conserved. Now, is this something acceptable? No, because so if you use MV, the usual definition, you would end up with something that is not conserved. What did we do wrong? Well, what we did wrong is that, yes? Please. Okay. Which one? This picture. We are moving with the speed of the velocity, so we are across particle 2.
Okay, so wouldn't I see particle 1 moving towards me?
Yeah, you're seeing particle 1 moving toward you. And there is not anymore any component along x.
Which direction is this?
This one is the y direction. Okay, so you always, so you are across particle 2. Okay, you don't have any x component, but you always see the other particle, even if when you were in the other direction, coming toward you. Okay. Of course, it's a very approximate picture, but you know you should stick to the numbers, and then the numbers tells you this. Now, what did we do wrong? That there is here the consequence is non-conservation of momentum. So what did we do wrong? Well, when we change frame, we have to be careful because we have to change also the time. Oh, you will find in the note, okay, the same. Sorry, I don't have space otherwise. Yes?
So because the note we are not able to read this note. That's why we want to write this.
Oh, that's, I understand. Okay, I understand. I understand. What should I do? Rewrite everything? But as I said before, maybe you were not. Let's schedule maybe before even the end that we will go through the notes. That means I'll sit down and I will read the notes so that, I mean, if you follow, there is a word that you don't understand, then I tell you which is the word that you don't understand.
For me, all of the word, I cannot able to read them.
Okay. So that means, what did you say?
We should go slowly.
Okay, I'll go slowly and reread the things. But I think the best is that really if you want that we do class by class in the sense that we take the notes of yesterday class and go through it. That means with the note in front, I will read, and so you understand what I mean. Okay, let's suppose I take the note I gave you out yesterday, okay, and we go through it in detail. That means you have your notes in front, I will read it, and then you will see which are the meaning of the various words. Okay, instead of copying everything, that's what I'm saying. That is something I was planning to do at the end of this, because the notes are only for 5 lectures or 6. It's not that all the course will be like that, okay? That's, and I apologize because I had to do it very quickly because I thought it was done. The notes, anyhow, I would say that among the book I suggested, the notes are very similar to what you find in the 3 books I suggested. Okay, so especially the Berkeley Physics course, Volume 1. Okay, so my notes are really mostly taken from that, with some small extra details, but not much that we can do, that I did. So the Berkeley Physics Mechanics, Berkeley Physics course Volume 1, Kittel and other is the authors. This is where I took most of the notes. No, but you suggest to me what is the best that we do. That I go slowly and you take notes from the blackboard, or that we sit down at the end of these 5 or 6 classes and reread the notes. And you take the notes, okay. Okay, then we can go over again. Let's go over this one again. Okay, so, so the concept is to define the momentum, and in the rest frame, we add this particle 1 moving with velocity v, so minus vy minus vx, and you have particle 2 moving in this direction with velocity v. This is particle 2, this is particle 1, and this has a vx and a vy, and when they scattered, they hit each other and move away in this manner, v, okay, so this is particle 2 that does this, and this is particle 1 that does this. Sorry, this is particle 1. Let's me just 1 and 2. Okay. Now, in this rest frame, so this is frame S, is at rest, the particle moves. The P at times T, the total P momentum at times T, if we define P as m times V, is 0, because you see one momentum is equal to the other and opposite, so this is 0. After scattering, the total P at times T equal T. After scattering, okay, again, the velocity is the same, it has only changed angles. This is coming in this direction and it goes into this direction. This is a simple exercise in mechanics, in relativistic mechanics. And again, the total P is 0. Now, if we look at the change for particle 1, let's look at the change for particle 1 in the y component. So we have to take particle 1 that here at times delta P means the P at this time minus the P at this time, but only the y component. Then looking how it is 2m vy. Because this vy is positive, I have to subtract from this, that is at time 0, so I get vy minus vy, it gets this, and the delta P2 for the particle 2 is here. This is the velocity. Then the y component is negative, and we get minus 2m vy. Now, you see that the variation of the two, if you sum the two, is 0. So the sum of these is equal 0. Now I said, let's analyze, and so everything is fine in the rest frame. The momentum is conserved, and everything is okay. But now let's go to another frame, S prime, and this S prime moves with velocity Vx. Okay, so the velocity of these is Vx, of the new frame. Then what... yesterday we derived a formula that tells us how the vertical component of the velocity change when you go to a moving frame, and the formula we got is that the v prime y is equal vy 1 minus vx, v, the velocity of the two frame, over c square minus 1 over v square c square. Okay. Now, as we said, the velocity of the two frame is Vx. So basically, if we take this formula and now adapt it to particle 1, let's take all the ingredient of particle 1. Particle 1 has a Vy that is minus Vy. So we get minus Vy. Then we have 1. Then Vx of particle 1 is negative, is minus Vx, so we get plus Vx. Then V is Vx, so we get Vx square over c square. And then we get 1 minus Vx square c square 1/2. I've just used this general formula and adapted to particle 1 and particle 2. Now let's do v prime 2. So this is the new velocity in the new frame, and this is the vertical velocity of particle 1 and particle 2. Now, particle 2 has a Vy that is positive, so I put a Vy that is positive. Then I have minus. Let's see, particle 2 has a Vx that is positive, and the V, the relative velocity, is positive, so I have minus Vx square over c square, 1 minus Vx square c square 1/2. So the picture is that the two particles now are moving in this frame at different velocity. You see they are different, the two velocity. There is a difference, a plus and a minus here, beside the sign there. So basically we have m for particle 1, m v prime 1, and m v prime 2. This is at time t equals 0. Okay, so basically this particle, as we are moving with velocity, we are in the frame in which we move with velocity Vx, there is only y velocity, and this is the other particle, particle 1 coming, but you see the length of the two are different. After, they will just move in this manner. After scattering, they will move in this manner. Okay, with the opposite direction than before. So this is at t equal time, after scattering has taken place. Now, where should I cancel? I don't want to cancel while you are taking notes. Where should I cancel? Tell me. This one I can cancel now? Okay. Okay, now if you look at the delta P of particle 2, you get 2m, the change in particle 2, 2m Vy2, and the delta Py of particle 1 is 2m Vy of 1. But as they are not equal, and opposite to each other, if you sum these two, you get something different from 0. That means in the moving frame, the momentum is not conserved. Okay, so in the moving frame, is not, let's say, seems not to be conserved. So this definition that is very similar to the non-relativistic one, mass times velocity, momentum seems not to be conserving going from one frame to the other, and this is something we cannot accept. So what we will do? Well, we have moved into, we have to look carefully at these things, because what we have done, we have moved into a moving frame, and then we have to change time. That means the new time in the moving frame is not as before, but it will be delta t 1 minus v square over c square. Okay, so the velocity that we should use should be the following. The velocity along y should be delta y over delta tau. And this is delta y over delta t 1 over 1 minus v square c square. So that is where we made the mistake. The mistake was we did not change the time in the definition of the new velocity. In the moving frame, this is Vx, okay? In the moving frame, the interval of time is different, it's this one. So now, if we define the momentum as m Vy, what we get is m delta y delta tau, and this is m. Now, this is the usual velocity, Vy, but there is this correction factor, 1 minus v square over c square. Sometimes people indicate this as saying the mass depends on the velocity plus this factor we call mv. So mv, we define it as m over 1 minus v square c square. This speed is better? Okay. Now, as homework, on page 6, I wrote down homework. With this new definition of momentum, redo the analysis we did here, and you will see that it's conserved. But there is a further reason why it is conserved, why it should be conserved now. This quantity now, remember, these things is this time. But this is the time you measure when you move with the particle at the same speed. So this is the proper time. This is a relativistic invariant. Okay? Remember the things before. The proper time coincides with the time you measure when you are going at the same speed as the particle of which you are measuring the velocity. Okay? So this people say in technical language, is a covariant quantity. This does not change, and what changes is only delta y, okay? But if you want to convince yourself that now momentum is conserved, as homework, take this expression of the momentum, redo that kind of analysis I did, and you will see that the momentum now is conserved. So, can I cancel here now? So the relativistic momentum, yes?
Could you explain a bit, say something about covariance?
We will go more in detail later on. We will go into it. I mean, I just give a hint, but I will explain. So the momentum was m v 1 over v square over c square. It means, you see here, as this does not change, this is a relativistic delta tau, is the proper time, so it does not change from one frame to the other. Then this v and the corresponding p transform as delta y. Okay, so it transform like x, z, and y transform under a Lorentz transformation. And those are sort of pseudo-vector. They transform, they transform with that minus sign, but they are component of a vector. We will get slowly into that because it's not an easy concept. So also the momentum should be a vector in this framework. Let's take the square. Now, you remember that basically we had an invariant before that was x squared minus c squared t squared, or delta x squared plus c delta t squared. The question is minus. Might it be, as the velocity and the momentum are just, they change under Lorentz, things only as delta x or delta y and so on change, that out of P I can build something that is invariant? The answer is yes. Now I will show to you that out of P, combining with some other quantity, you can build something that is invariant. Look at this identity, 1 minus v squared c squared minus 1 over v squared c squared. This quantity is 1, right? So the calculation is 1. Multiply now this by m c to the fourth. Multiply all this by m to c to the fourth, and what you get is m squared c fourth over 1 minus v squared c squared minus m squared v squared c squared 1 minus v squared c squared equal m squared c to the fourth. Now, this one, so I have taken this identity, multiplied by m squared c squared, c fourth, I get this expression. But now, this you recognize immediately what it is. This one is related to this. This quantity, so this expression, so I have m squared c to the fourth, 1 minus v squared c squared, and this expression is nothing else than p squared c squared equal m fourth c fourth, m squared c squared. So I have rewritten this because this quantity, if you look, is nothing else than p squared. There is something wrong. P squared No, it's okay. If you look at this term and look at the dimension, this is the dimension of energy because it's a momentum, an energy square, because it's a momentum times a velocity as the dimension of energy. So let's take the following definition of relativistic energy, these things. So this is a definition of relativistic energy. And why it makes sense? Well, if you expand in V over C, considering V over C small, it's easy to see, do this problem. This is nothing else dmv square plus mc square plus term order V square C square. So you see, you have the kinetic energy, the non-relativistic kinetic energy, and another constant term. This is E, not E. This is E square, and this is E. Okay, so if we take these as definition of energy, it is a reasonable definition of energy because it has the usual kinetic term plus a constant term, for the moment we don't care, plus a lower order correction. So what happened is, now I cancel here. No, that one. I cancel here. We get that relation, this relation over here, this relation over here can be written as the following. E squared minus P squared C squared is equal M squared C to the fourth. Okay? And look, and E, that has that expression, 1/2 mv plus mc squared plus correction v over c is very important because now if the particle does not move, if it is at rest, so let's take a particle at rest, you get that E in this expression is mc squared plus correction and so on. That means this is the pure kinetic energy, and this is the mass energy. And you can get it from here. If the momentum is 0, if P is 0, what you get is that E is equal mc squared. And this is the famous relation, Einstein relation, that was not in the original paper, but was later on, that somehow this definition of energy, that is somehow a good definition, when it contains the kinetic part and the mass term, when there is no motion, there is actually, due to the mass, a content in energy. Is this definition, is this fact something known? Yes. It is known because it has been verified later on. You know, at the beginning, when Einstein proposed it, it looked a little bit crazy. But, you know, in phenomena like fission, you have a nucleus that breaks down into two smaller nuclei, M1 and M2, where M1 plus M2 is less than M0, and what happened? They have a lot of energy. Part of the mass in the difference is emitted as energy in the fission, and the same result also in case of fusion. You fuse two nuclei like hydrogen, and you get a heavier nucleus, but with a mass that is less than the sum of the two. It means some energy has been lost. Okay, but in fission is the typical example where you have that some of the mass is converted into energy with this relation. And you see where it came from. It came from this identity, using this identity and this definition of energy. You might just say, well, I don't like that definition of energy, it's a doc. But you know, it's a definition of energy that goes exactly in the non-relativistic limit into the kinetic term plus extra piece, and that is what we wanted. Second, this relation is really the analog of delta x or delta t square minus delta x square c square equals 0. You know, this quantity was an not equals 0. This quantity is an invariant, a relativistic invariant. It does not change when we move from one frame to the other. The same here. You see, this is exactly the analog. This is something like the t component of a vector. This is something like the x component of a vector. And this quantity is invariant. Okay, so this is another, together with this, invariant relation, invariant under Lorentz transformation. Please.
Okay, we know, we are familiar with the first two terms, but yeah, those half m v square, but we don't know, okay, what those high order corrections really imply.
Oh no, the other correction, you see, if you are non-relativistic, v is very small, you can neglect them.
But okay, let's say v is comparable with c.
No, then in that case, you have to use this formula. Okay, you have to use this formula, and this is the total energy. So this is the total energy that a particle has if it moves at a velocity v that is comparable with c.
Okay, now, okay, let's see. Okay, v over c is much less than 1.
If v over c is much less than 1, then you get this expansion.
Okay, and then, okay, we want to go up to the third order correction.
Mm-hmm.
And then what is the third order correction?
The third order correction. You have to calculate it. It's just very simple.
Does it have any physical meaning? I just want...
Yes, this physical meaning is basically the correction, not to the mass, but is the correction to the kinetic energy. So, because it depends on the velocity. So, if you ask, which is the relativistic kinetic energy? The relativistic kinetic energy is not just this, but is this plus the extra term, the kinetic energy.
Yeah, okay. We are in the limit when v is much less than c.
If we take that limit, then
okay.
there are these extra terms that you can neglect. Okay?
Yeah.
You can neglect. If you don't want to neglect, then you have to add to them. But if you don't neglect, it means v is not so much smaller than c. You have to add to them, and then you have the total kinetic energy in the relativistic limit.
Yeah, so even if v is much less than c, we still have the correction. But
Yes, of course, it depends if you consider them, you know, if v is much smaller than c, then you don't take this extra term, okay? So you take it if v is not so small than c. Any other question? Now, please.
If V0 with some order corrections here.
I don't understand.
If V0 there, we have,
Only the mass term.
so there is no this order correction.
No, I mean, I just said if this v is 0, of course, that you don't have also that, and then you have just the mass term. Now, one thing I wanted to say here, please,
one more.
please.
Can we use this equation which relate the energy, the mass, and when v is c,
No,
when speed is c? Can we use this thing when v is c?
Oh, when the velocity is c,
Yeah.
when we are at the speed of light. But then, let's remember what happened. You see, if v goes to the speed of light, this becomes 0, and then the mass goes to infinity. So the inertia when you go to the speed of light is infinity. The only manner to avoid that is that this is 0. Okay? Then if this is 0, and then this... so if the rest mass is 0, so that means when we go to the speed of light, either the inertia become infinity, or otherwise we have to take that the original mass is 0. Then if this is 0, okay, this is the usual relation for a photon. Okay, that means E is equal to PC.
Yeah, because I asked this question, if we take V to BC, then the identity is normal, right?
Right. Okay, let's now go back to what he asked before. Can I cancel everything? Now, the next question that we will address is, if we do, as these EMP are linked in this manner through an invariant relation. Invariant, it means this quantity does not change under a Lorentz transformation. So also this quantity does not change. That means if I go to a moving frame, these things should remain the same. And so on. This should remain the same in any frame, because these quantities are just numbers, and we know that the velocity of light does not change, and this is the coefficient we gave to the mass of the particle. So this is an invariant quantity like the one above. Then if it is invariant, the EMP should change in a proper manner in order for this to be invariant. So that means when we go from one frame to another, this should change in a proper manner. And it's easy to see how it changes. Let's remember Px is defined as dx, but here we put the d tau, the proper time. And the proper time is the time that is invariant. You know, the proper time is this quantity, and is invariant under Lorentz transformation. Py is equal n dy d tau. Pz is equal n dz d tau. You see that this object, this momentum, will transform under Lorentz as dx, because it's the only quantity that changes. This does not change. It's a proper time. Py change according to dy. Pz, because all the other quantities don't change. Look now what E, or you can write E. We had the expression of E in the previous blackboard, and it can be written in this manner. Why? Because this quantity is nothing else than 1 over 1 minus v squared c squared. So we could write the energy in this manner, dt over d tau. Why? Because it is this quantity, and the energy we know that is mc squared divided by this. But looking at it in this manner, this is invariant. It means the energy transforms as an infinitesimal interval of time. Okay? So you see we have got another object that is isomorphic to dx, dy, dz, and dt. So it will transform as this quantity do. In fact, from this expression, let's do a Lorentz transformation. Then you have to change dx, dy, dz, and dt, and automatically you will get a change in px, py, pz, and d. What you will get is the following set of transformations that are very similar to the one you have already seen for x and y. That the new px, so we suppose we move along x, is px minus e v over c squared divided by 1 minus v squared c squared. Py is equal to py. You know, it does not change anymore. Note, pz prime is equal to pz, and E prime is equal to E minus pxv over 1 minus v squared c squared. So if I ask you, how did you derive these things? Well, I derived by using this expression and knowing how x and dx change under a Lorentz transformation. So x, y, z, and ct make what is called a 4-vector. We will get to that. And the same px, py, pz, and ec makes another 4-vector. Now, this definition of energy that we gave is not only nice because it makes, when you, in a relativistic limit, you have the kinetic term plus the mass, the energy of the mass and so on. But this energy is conserved in any frame, like this one was conserved in any frame. We started this lecture proving that if you use dx dt, then this would be conserved only in the rest frame. It would not be conserved anymore in the moving frame. If you use this other one instead, it is conserved. The same for the energy. This strange definition of energy is an energy that is conserved in a scattering experiment. Now, I wanted to, when I said this is a 4-vector, let's see in which sense is a 4-vector. Can I cancel somewhere? There. Before we introduce the concept of a metric, something like G, let's put the Greek index mu nu, delta x mu, delta x nu, and this is a proper distance. And for example, when mu we can indicate with a Latin letter, then it is 1, 2, 3, or we can indicate with a 0, and this is the 4th component. Okay, so in this case, to get this kind of object, okay, we can say, well, G mu nu is a matrix that is done, the 0, 0 component is 1, the other are minus 1, minus 1, minus 1. Okay, but we can do much simpler things. So this is the relativistic case, and this is basically the proper time, if you want. There is something like this that is the, in the non-relativistic case, so this is the relativistic case. In the non-relativistic case, you can have distances, and they are defined Gix, delta xi, delta xj, square root, where now the Gij, or let's say delta L, is 1, 1, 1, and this is nothing else than square root of delta x square plus delta y square plus delta z square. Now you see that here, somehow, this is a 4x4 matrix, and this is as an index, so it's a vector, and is delta x0, delta x1, delta x2, delta x3, that are x, y, z, and this is ct. Okay, so basically we multiply these by this kind of vector. So in this sense, this is a 4-vector. in the sense that it's an object that has an index and it gets contracted with the metric in order to give a distance. But there is also another sense in which it is a vector. Let's take non-relativistic and let's take a rotation along x, along z. So let's take non-relativistic thing z, x, y. Which are the transformations that preserve the length? Are the rotation, right? So if we want the transformation that preserve the length, for example, let's do rotation along z. The rotation along z, you have x prime is equal x cos theta plus y sin theta, and y prime is equal minus, never remember by heart, minus x sin theta plus y cos theta. This is a normal non-relativistic rotation, but it preserves x squared plus y squared plus z squared is left invariant. Okay, this is the non-relativistic case. In the relativistic case, these four vectors, this quantity, the length is this. Under what is left invariant? Under the Lorentz transformation, right? So this is this answers your question. When I say covariant, it means there is this object whose components are these. If you do the length square, is the length of a vector that is left invariant, like the length of a vector is left invariant by rotation. This is a 4 vector because it has 4 components. It has this strange metric, but is left invariant by Lorentz transformation. So the analog of these, so this is no, so it's a rotation along x. Now let's take the relativistic case. In the relativistic case, we have x prime equal x minus vt, 1 minus v square c square, then the other left the same, and t prime is equal t minus vx c square, 1 minus v square c square. For this transformation, that is a Lorentz boost, we know that what is left invariant is t square minus del x square over c square is left invariant. You see, this is like a distance, but it has a minus sign. In fact, the metric that gives me the distance has this strange minus sign. So the Lorentz transformation can be seen as a sort of rotation, but in a space in which the metric and the length are defined with this minus sign that are this. Did you have any question? Yeah. That this will become clear as we go on. And this is just the beginning of these things. Actually, it is easy to see that this transformation can be put in a form very similar to that. This transformation can be written not with sine and cosine, but with cosine and sine hyperbolic. This one can be written in a form very similar to that, where t takes the role of y and x. It can be written in this manner. Let me see. X prime is equal to minus, no, let me write it here, sorry, I don't know where to go anymore, no, here. This transformation can be written in this manner, x prime, t prime is equal to x cosine hyperbolic of psi plus t sine hyperbolic of psi t prime minus this one x sine hyperbolic of psi plus t cosine hyperbolic of psi, where psi is nothing else than, okay, let's put it this way, cosine hyperbolic of psi is equal 1 minus v squared c squared. But now you see the strange similarity. One is with cosine and sine, the normal rotation along z, in normal x, y, z space, while in xt space, the Lorentz transformation is very similar to a rotation, but with cosine hyperbolic and sine hyperbolic, okay? I ask you to check, using these things, this relation. Okay, let's stop here for today.